quickly, to continue the previous example, I forgot to show you the code. So in Oscar, you can very easily compute the ideal of a toric variety. So the command is toric ideal. The syntax requires you to transpose the matrix. So you can compute the degree. It is 3. That's the volume of our triangular prism. We have, I make the polytope P by appending a column of zeros to the matrix A. I compute its convex hull. And I check that the lattice volume is 3. Lattice volume means normalized volume. Okay. Then I can make the ideal defining the Birch point. So that's the toric ideal plus the linear ideal of AX minus B. Compute the solutions and I get a similar output as before. There are 3 solutions. The variety has degree 3 and only one of them is positive. That's the Birch point. Okay, and then there's similar code for the entropic sheet. But let's move on to the semi-definite part. I'll put this up for the time being and we'll get back to the slides near the end. Okay, so 2 semi-definite programming. Okay, and I'm sure all of you know better than I do that semi-definite programming is a generalization of linear programming. The notation is, so this looks like a $sign, but it's the symmetric matrices of size n. The wrangle will be the inner product, standard inner product. So inner product between A and X is the trace of A times X. So usually you would write A times X transpose, but the matrices are symmetric, so that doesn't matter. Okay, so this is the, you can think of this as the usual inner product on R to the n squared. Okay. Sn plus is the PSD cone. So these are the symmetric matrices for which V transpose XV is non-negative for all V. Okay. What's a semi-definite program in standard form? The game is to minimize a linear function w dot x subject to the constraints I'm going to fix D matrices, D symmetric matrices A1 through AD. Impose the constraints that A1 dot x is B1 and AD dot x is BD. For some real numbers, B1 through BD. Thanks, yes. So previously x was non-negative. Now x is positive semi-definite. Thanks. Okay, I'm going to write, so I'm going to abbreviate this by writing pi of x. I'm going to view this as a linear projection of x and write this as pi of x as b to make my life easier. Okay. So if we only allow diagonal matrices, then this is a linear program. This is the same linear program in standard form that we were studying before the break. So this is a generalization. Okay, the name, so the feasible region now is not necessarily a polytope anymore. It's a generalization of polytopes called spectrahedra. So the feasible polytope, which is Sn plus intersect pi inverse B, is a spectrahedron. It's the definition of a spectrahedron. It's this affine slice of the positive semi-definite cone. Okay. Example. So famous example of a spectrahedron. Well, I should share this with, I know I'm sharing. Next slide. Okay. So this was on Victor's slides. I don't think we talked about it much, but I think it's interesting to talk about this picture. So famous example of the spectrahedron is this samosa-shaped figure that you see here in the middle. The boundary of this samosa is a cubic surface, and it's given by that very nice equation. So you can expand the determinant, get a polynomial in x, y, and z. That defines the boundary of this elliptope. It's called the elliptope. It's an example of a spectrahedron. Okay. So the inequality for the inequality description of this spectrahedron is precisely that matrix is positive semi-definite. Okay, so you can see from that it's an affine slice of the PSD cone of 3 by 3 matrices. Okay, it's the affine slice given by diagonal equal 1. Clear? Okay. Okay, so the algebraic boundary of this is also very interesting. Henry, where's Henry? Do you remember what the boundary is called? It's a surface and it has a name. Yes, very good. Okay, so we discussed this over pizza and IPA earlier this week. So this is the Cayley cubic surface in 3 space. So it has the maximum of 4 singular points, and it's the up to projective transformation is the unique cubic surface with 4 singular points. So it's also interesting in complex algebraic geometry, and the Cayley cubic surface is the algebraic boundary of the elliptope. Okay. So that's just an example of a spectrahedron. I will, similar to the linear programming case, I'll make some assumptions to ensure that our spectrahedron is bounded and compact. So I will assume, first of all, that the problem is feasible. So B lies in the projection of the PSD cone. Otherwise, there could be no point in our spectrahedron. This means non-empty. And then I will require that the linear span of our matrices A1 through AD this is a linear space of symmetric matrices. So some people call this LSSM. Okay. Linear space of symmetric matrices. I will assume that this contains a positive definite matrix. Okay, and I'll leave this as an exercise, but that assumption ensures that our spectrahedron is bounded and therefore compact. Okay, and that has the advantage that our minimizer exists for any W. Okay. And we're going to regularize this, right, just like we did in the linear programming case. So the picture is this. So now the feasible region, it looks a bit more curvy. It's a bit like a polytope, but it could be something more curvy. This is a spectrahedron. We still have a linear function that we are optimizing. So there are these level lines, and there's going to be some optimizer. It's not necessarily in one of these corners. Could have been somewhere on the boundary. Yes. Oh, thank you. Sorry. Very good. Thanks. Yes. Okay, this is a linear space of symmetric matrices in the vector space, not in the cone. Okay. Yeah, so the optimizer is going to lie on the boundary of our spectrahedron. This will be the X star. But now we regularize. We're going to be minimizing Wx plus epsilon h, where h is going to be strictly convex on our spectrahedron, just like before. Okay, so now the picture becomes something like our X star is going to depend on the regularization parameter epsilon. If we drive epsilon to 0, we're going to go back to the original optimizer. And there is some distinguished point X star infinity that only depends on our choice of H. It doesn't depend on W. And there's an optimal path in green. That walks from X star infinity all the way to X star of 0. And the level lines of our regularized objective function, they look something like this. The same picture as before, but a bit more puffy, a bit more nonlinear. Okay. If there's no questions, I will go to 2a. Okay, this is regularized semi-definite programming. Solving the semi-definite program like this is an interior point method for solving STPs. 2a, logarithmic barrier. So here I'll be very short because I don't know much about this. And I don't know how much is known, actually. Maybe if you know, you can tell me. But so someone who would know more is Mateusz, I think. And so Mateusz told me earlier this week that Jan Drijsma has worked on this, at least on the varieties that will pop up. But I can't point you to a paper. So we want to minimize the following regularized function. So this is the analog of the log barrier from before. Now I take the log of the determinant, or equivalently, the trace of the matrix logarithm. Okay. So this minimize x PSD subject to our linear constraint. First order optimality. Again, 3 cases. Fixed epsilon, epsilon to infinity, and all epsilon. Okay, so for fixed epsilon, the gradient of this function is still x inverse. Okay, that's something you have to wrap your head around, maybe. But that's why everything goes through very similar to what we did before. So the gradient of log det x is x inverse. So if you write down the first order optimality conditions, you find that x inverse lies in the affine space of symmetric matrices given by 1 over epsilon times our cost matrix W plus our LSSM. Okay, I'm being liberal with the notation. So I arrange the vector into a matrix. Okay, so the derivative with respect to xij is the ij entry of the inverse. Okay. Questions? Okay, so first order optimality for fixed positive epsilon is that X inverse lies in the affine space of symmetric matrices given by our LSSM, linear span of the A matrices, plus W over epsilon. Okay, epsilon to infinity says that X inverse lies in L. And for all epsilon, you get that X inverse lies in the linear space of symmetric matrices generated by W and L. Very similar to what we did before, except we're taking the reciprocal of a linear space of symmetric matrices. So in our linear space of symmetric matrices, we take the matrix inverse of every point, okay?
If I may just a comment, the names that appear there, they study this variety of inverse. I don't know if certainly not means that logarithmic variety. The variety of inverse.
That's right, yes. So I don't claim that they write about regularization in their paper, but so earlier this week I asked Mateusz what's known about these reciprocal spaces. And he pointed me to a paper by Jan Drijsma and co-authors. Okay, so the sentence I was going to write is that the varieties of interest here, so if you want to regularize in this way using the log det, then the varieties of interest are reciprocal linear spaces of symmetric matrices. And as I said, this is the section I know least about, so I'll be very brief. I'll just give one more example and then move on to entropic. Okay, so also here's an innocent looking matrix of prime numbers. And I'll use three matrices A, we go, and B is 433. Again, feel free to solve the SDP and let me know what the optimizer is. So for the regularized SDP, if we want to compute the analytic, let's call it the analytic center, right, of the spectrahedron, in analogy with what we did before, we need to write down the equation of a reciprocal linear space of symmetric matrices. And here's how you do that. So I can define a generic matrix X, generic symmetric matrix X, like this. And I will define a generic symmetric matrix Y that lies in our LSSM. Okay, so how do you define that? Well, it's a Y1, A1 plus Y2, A2 plus Y3, A3. So that gives you this on the diagonal. And this on the off diagonal. This is a generic matrix in my LSSM. Okay. How do I compute the reciprocal? Well, I construct the ideal matrix product X times Y is the 3x3 identity. And I eliminate Y. Using Grobner basis resultants, anything you like. I did this, and our reciprocal linear space of symmetric matrices is as an ideal generated by 6 quadrics. You can check. And with Oscar, you never really know if this is minimal. So I don't know, maybe these quadrics are linearly dependent. So this is dimension, I'll ask you. It's the dimension of L inverse. Presumably 3, right? So I take the linear SSM, I just take the inverse of all the points in it. That will preserve the dimension. So this has the same dimension as our LSSM, which is 3. Degree is 4. This I computed. And if you compute the reciprocal of this, it becomes dimension 4 and it keeps degree 4. Okay. That's all for the logarithmic barrier in semi-definite programming. You can make it symmetric, right? You can make the same linear function by symmetrizing W. You can assume W is symmetric. I should have said this. Okay. Okay. Mm-hmm. Oh, good question. I don't, it's been a while since I studied the dual SDP. Does anyone know? If the Y here is related to the dual SDP. I think so. So in the case, yes. So for instance, in the SOS case, this LSSM would be the Hankel matrices. So I think so, yes. Okay. I want to do that example also at the end. Right, so 2B is entropic regularization. And this comes from a paper with Dmitry Pavlov and Bernd Sturmfels called Gibbs manifolds. So this will, the analog of the reciprocal LSSM will be a Gibbs manifold in this context. Okay, what's the entropy function here? So we're going to minimize over the PSD cone Wx plus epsilon trace of x log x. So before we had xi log xi minus xi, this will be the trace of x log x minus x. That's the correct generalization. So again, if x is diagonal, you recover exactly the entropy function from before. So this is a version of the von Neumann entropy of a symmetric matrix. Just to remind you, so the matrix logarithm, we write the constraint first, we still want phi of x is b. So the logarithm you define using the familiar series expansion, which goes identity minus, oh no, x minus identity. Okay, so first thing that actually requires maybe a bit of work, at least this was not obvious to me, is that this function, this entropy function, is strictly convex, first of all. On the positive semi-definite matrices. And its gradient, which is why we like it, is the matrix logarithm. Okay, that's mainly why we choose this function. I promise this is the last time we do first order optimality. What does first order optimality tell you? So using this proposition, you find that, so the gradient with respect to x gives you w plus epsilon log x is lambda transpose A, which now means lambda 1 A1 minus lambda DAD equal to 0. For fixed epsilon, this means that the logarithm of x lies in a affine space of symmetric matrices. For epsilon infinity, this means that log of x lies in L. And for all epsilon, you have that the log of x lies in the span of W and L. Okay, this by now is routine, okay. So if we want to study this kind of regularization in the way we did in all the other scenarios, this tells us that we should think about manifolds that arise as the matrix exponential of linear spaces of symmetric matrices. Okay, so this says x lies on the matrix exponential of L. That motivates this definition. The Gibbs manifold Gm of L in general, L can be an affine space of symmetric matrices. So the affine space is called L, is simply the matrix exponential of L. So this is a manifold contained in Sn plus. Okay, in the interior of Sn plus. Matteo. Yes, agreed. Okay. Right, so take any matrix, any real symmetric matrix, apply the matrix exponential, you'll get a positive definite matrix. Okay. The Gibbs variety is the Zariski closure. And we like to think of complex varieties. So the Zariski closure in symmetric complex matrices.
I think there's other exponential map. This is can also have with the algebras.
Yes. Yes. Don't ask me how, but
Of the points, like I guess the differential, it's to get the image of this exponential map, and it's probably smooth because it's the exponential map.
yes. So the matrix exponential is a diffeomorphism. So this will still be diffeomorphic to L.
Then provide closure potential, you have some singularities.
In the closure, you potentially have singularities. Okay. Okay, so here's I'm gonna call this theorem, but we basically already proved it. This is a reformulation of our first order optimality condition. So the maximizer, is that what I mean? Yes. So the maximizer, X star infinity of the von Neumann entropy. And I think I made a mistake. Okay, this is minus the von Neumann entropy. Okay, so minimizing this means maximizing the entropy. Okay, so the maximizer of the von Neumann entropy on the spectrahedron by inverse B is the unique intersection point of the Gibbs manifold with the spectrahedron. That's why we're interested in this object, right? So the Gibbs manifold, it parameterizes all the entropy maximizers. So as you vary B, so the spectrahedron depends on B, right? You vary B, you change the spectrahedron, but for every choice of B, there'll be one intersection point with the Gibbs manifold, and that's your entropy maximizer. Okay, and the name is motivated by Gibbs distributions, which are probability distributions that maximize entropy. Here's the picture. This is not the example we had been doing before. So this is another 3x3 example where A1, A2, and A3 fix the diagonal entries of the matrix. Okay, so imagine that I choose B1, B2, and B3 to be 1, 1, 1. That means we're looking at the elliptope. Diagonal equal to 1 means we're inside the elliptope. And then there's one more matrix, A4, that imposes one more linear condition on the elliptope. Okay, so you take a slice of the elliptope, you get the green thing. So the green oval is our spectrahedron. Okay. The Gibbs manifold is a curve in this picture. Okay, so Gibbs manifold looks a bit linear on the left, right? So that's this blue thing that looks linear. It intersects the green spectrahedron in precisely one point, and that is called, we call this the Gibbs point. It's the analog of the Birch point and the analytic center and so on. Okay, this is the Gibbs point. Now what happens when you drive epsilon to, when epsilon is not infinite, but epsilon becomes finite and it approaches 0, what happens is that this Gibbs manifold degenerates. So in the picture, everything stays the same, right? We're not changing the spectrahedron. What changes is the thing we need to intersect with. So this epsilon starts moving. It comes back from infinity to finite numbers. So the blue curve degenerates. And as epsilon gets closer and closer to 0, the intersection point with the spectrahedron gets closer and closer to the minimizer of the SDP, which is the little blue dot that you see on the right. Okay. That's the geometric picture. Questions about this? Okay. Mm-hmm. No. So very good point. This I'm calling this Gibbs manifold is not semi-algebraic, if that's what you're pointing at. So the Zariski closure of the Gibbs manifold may have larger dimension. Even if the A's are defined over Q. Does that puzzle anyone, or? So usually, I mean, you would expect that you apply transcendental functions to linear spaces. Why would the result be algebraic? So somehow if you take a linear space that's defined over Q and you apply the exponential, you get a toric variety. If your linear space was not defined over Q, the same thing happens. The Zariski closure of the image will have larger dimension than the dimension of the original linear space. Yeah, and so here this is, even if the matrices are defined over Q, the matrix exponential doesn't need to give you something semi-algebraic. But in some cases it does, so I'll give examples where it does. Okay, so the next sentence in my notes was Gibbs manifold is in general not semi-algebraic. But on the other hand, it's also not so bad. So the dimension of the Gibbs variety could in principle be n plus 1 choose 2, the dimension of Sn plus, right? But that is usually not the case. So the dimension of the Gibbs variety is at most n plus d. So the dimension of L is d, and in the worst case, you add n to it. It's not quadratic in n ever. Okay. Better yet, so if L is not affine linear but linear. So if L is a linear space of symmetric matrices, not affine space of symmetric matrices, then the dimension is 1 less. It's at most n plus t minus 1. This you can show. And these bounds are tight. So you expect actually the dimension to be this number if you pick random matrices. What's the idea of the proof? The idea is that you can parameterize the Gibbs variety as follows. So you need a bunch of parameters. You take the parameters y1 through yd, which play the same role as the y's here. So these y's parameterize they are coordinates on L. And for each point in this linear space of symmetric matrices, you keep track of the eigenvalues of that matrix. So we have n eigenvalues. And you introduce some extra variables z1 through zn that you should think of as the exponential of the eigenvalues. Okay, in your mind, these are the exponentials of the eigenvalues. You take all points with 2n plus d coordinates that satisfy, this is a bit problematic notation. So I want that the coefficient, the ith coefficient of the characteristic polynomial of that matrix is equal to the elementary symmetric function and the eigenvalues. So I want these lambdas to correspond to the eigenvalues of the matrix Y. Okay, so I want to impose that the ith coefficient is up to assign the symmetric polynomial in the lambdas. Polynomial equation in my variables. Okay, so this is a variety of dimension d plus n. And it parameterizes our Gibbs variety. So you send this to, and this is based on a formula that was observed by Sylvester. So it's a very old thing. I'll just write it for completeness. So this is lambda j minus lambda I times your matrix A of y, which is that matrix, minus the identity. Okay. So this gives you see that the Gibbs, from this, if you believe me, you see that the Gibbs variety is parameterized by a variety of dimension d plus n, so it could not have a higher dimension. Example. So we continue this example, so maybe I erase this. This is our example from before. What do you expect the dimension of the Gibbs manifold to be? So in the Gibbs manifold of this LSSM. Who's still awake? Anyone except Mateusz? Yes. What's n? Oh, I hope you know what n is. We're doing optimization over n times n matrices. What is n?
3.
Thank you, Joshua. Okay, n is 3. What is d? What's the dimension of our LSSM? 3, thank you. What is n plus d minus 1? Thank you. It's a hypersurface in the 6-dimensional space of 3 by 3 symmetric matrices. And I'm going to write for you the equation. So the the Gibbs manifold as dimension 3. I'm sorry. The Gibbs variety is dimension 5. Right? Sorry, didn't mean to confuse you. So the Gibbs variety is a cubic hypersurface. And for concreteness, this is the equation. So it has a very nice.
It was not so trivial that we could ask immediately.
Sorry? That for the equation.
Guys, not to answer immediately.
Not to know the equation, yes, that's fine. I'll accept that you don't see the equation. Okay, so the variety of this expression. Exactly. So you don't see that it's a cubic hypersurface, but this theorem tells you expect that the Zariski closure is a hypersurface, and using this parameterization, you can compute it. And knowing this parameterization, you can compute that equation using variable elimination. So dimension is n plus minus 1 is 5. The dimension of the Gibbs manifold is 3 because the exponential is a diffeomorphism. And okay, so then I had this relates to Bernard's question. So how could you, suppose you want to find the SOS decomposition, sum of squares decomposition of a binary octet. So you have polynomial in T1, T0, T1. You want to write it as a sum of squares of quartic forms. How can you find D as a SOS decomposition of this thing of maximal entropy? So this you can phrase as an intersection of a spectrahedron with a Gibbs manifold. And I think I just wanted to mention this. I think for this audience, this might be an interesting exercise. So this spectrahedron of positive semi-definite symmetric matrices that correspond to an SOS decomposition of such a polynomial is called a Gram spectrahedron. It's a paper by, so I think this is Rainer Zinn, Cynthia Vincent, and maybe Daniel Plaumann. Okay. It's a paper called Gram spectrahedra. These are spectrahedra whose points are SOS decompositions of a given form. Okay. And the way to compute this maximal entropy SOS decomposition is you take the spectrahedron and you intersect it with the Gibbs manifold of an LSSM of Hankel matrices. Okay, so I promised to say a few words about quantum optimal transport. What's the geometric center?
The elliptic, there will be a center of growth. Like you can define a geometric as, for example, the maximum distance to all of the vertices, because suggestively you always drew it sort of in the middle of a hydra. I was wondering if there's a connection. For example, in the linear programming case, we have a hexagon. Then there's a geometric center, which is the center. But is the analytic?
I don't know what the center. So what the center of a hexagon is not so. So there's a barycenter, I guess. Yeah. Whether that's the same as the analytic center, I don't think so. I would be a little bit surprised. It sounds like the barycenter would be like the Santalot point, or the point that maximizes the dual volume. But I think that's also a conjecture. I'm not certain about this. Short answer is I don't know. I would be surprised if they're the same. I don't know if anyone has a better answer. Yeah, so there are different ways to define a canonical interior point. So any strictly convex function you choose, or any barrier function you choose will give you a way to define a center. Turn off the lights. Okay, so an example of a semi-definite program with a very nice Gibbs manifold is quantum optimal transport. And I'm using the definition from from this paper. This is Kohl, Eckstein, Friedland, and Zichkowski. Okay, so you minimize a linear function subject to the linear constraints that impose certain partial traces of your semi-definite matrix. So if you're doing this quantum optimal transport problem with parameters d1 equals d2 equals 2, it means you are optimizing over positive semi-definite 4x4 matrices whose partial traces are prescribed to be y and z. How do you compute the partial traces? Well, so you can compute the traces of these 4 blocks. That should give you a prescribed matrix y, or you could compute the traces of these 4 blocks, okay? So you could just partition the matrix into 2 times 2 matrices in these 2 ways, okay? Very concretely, in this example, the matrices A defining this projection give you this LSSM. So it's a 5-dimensional linear space of symmetric matrices. And the problem is feasible if and only if the trace of y is equal to the trace of z. Also, and the trace matrices should be positive semi-definite as well. Okay, that's the definition of the problem. And then by what we've been discussing, the Gibbs point, so that's the point x star of infinity, is the unique positive intersection of the spectrahedron with the Gibbs manifold. And the Gibbs manifold is the exponential of LSSM of A. Okay. And remarkably, so this is really something we were really surprised by, the solution to this intersection, so the unique intersection point has a rational expression in terms of y and z. So if you're given partial trace matrices y and z, you can just compute the entropy maximizer as y Kronecker z divided by the trace of y, which is the same as the trace of z. So this is a symmetric formula. In particular, this means that the Gibbs manifold is not only semi-algebraic, it also has a rational parametrization. So in this particular case, the Gibbs manifold is semi-algebraic. It's a semi-algebraic subset of the PSD cone. Here I just took a screenshot from our paper. Okay, so Gibbs manifold is a semi-algebraic subset of the PSD cone. It consists of all symmetric matrices that come as Kronecker products, and the Zariski closure is a Segre variety because it's has the same parametrization. I think you will forgive me for finishing 5 minutes early, and then we can end with questions.
Questions, comments, please. Manifold is quite interesting, but if we're thinking about semi-definite programming, why is the Gibbs variety of interest?
Yeah, very good. So Gibbs variety tells you some algebraic conditions that are satisfied by the optimizer, right? So if you can compute some constraints that hold for the optimizer, then you could add them to the SDP to shrink the feasibility region, for instance. Okay, I don't know how useful that is. So in many cases, there are actually some linear equations that vanish on this Gibbs manifold. So you can add linear constraints and reduce the dimension of the problem like this. Another motivation, I think, comes from this iterative proportional scaling that I explained to you. So as far as I know, there is no direct generalization of this to the semi-definite programming side of the story, right? So if there is an iterative algorithm that walks on the Gibbs manifold and converges to the entropy maximizer. And 2 years ago, I had an idea of how you should do that, and I implemented it and it worked, but I couldn't prove it. So it was not easy for me to generalize the proof in the linear programming case to the SDP case. That was a project I was going to suggest tomorrow. Yeah.
I think in this case varies for this particular quantum optimal transport on the slide. There is a version of scaling, solving implies scaling.
That could be. I'm not very aware of it. So certainly not of this quantum literature, but that's okay. That would be interesting to compare with. Yeah. So the algorithm I had in mind will work for general LSSMs. So maybe this is like a Sinkhorn version for a version of Sinkhorn for this quantum optimal transport. I see. Okay, thanks. That would be interesting to look at.
Right, it's the same dimension as manifold.
I see. It's interesting. Sorry.
Do we have any thoughts about hyperbolicity columns beyond the PLC column?
Oh.
Hyperbolic programming pattern beyond.
Haven't thought about it. It's interesting. I have not. So what would be the optimization problem, or?
So there is the hyperbolic polynomial that defines your hyperbolicity column. Then the natural area function is the logarithm of the polynomial. So that will be the envelope of the first. Right. The case.
The logarithm of where it's the logarithm of the determinant. You replace the determinant by the algebraic boundary of the hyperbolicity cone. That's interesting. I have not thought about it. Thanks.
Bernard asked you about the fact the matrix is said to have integer entries. And this kind of prompted you to say that the Gibbs manifold is not semi-algebraic.
Yes.
Why I didn't.
Oh yeah, I thought that was Bernard's worry. So I thought the reason why Bernard asked this was to make sure that maybe what I was getting was still a variety. And then my answer was that even if the matrices have rational entries, the Gibbs manifold is not semi-algebraic, which happens in our example, right? The Gibbs variety is dimension 2 higher than the Gibbs manifold.
Last question.
So at the beginning, we minimize some Euclidean product, then some trace of matrices. Is there a version where you minimize the contraction of two tensors?
So you mean you want to replace this linear term of the cost function or the objective function, or sorry? So
yes, we minimize the contraction of two tensors.
Instead of w dot x, you want to do contraction of something with x.
The trace of the Euclidean product. Has this been?
I don't know exactly what you have in mind, but it sounds still like a linear function on x. But then I see. Then you want the right analog of positive semi-definiteness, or?
Yes.
I see. So you're asking for a generalization of semi-definite programming. Yes. I see. I should not be the one. Good question, but I don't have a satisfying answer. Sorry.
Okay, so it's time to close. We thank again Simon for the excellent lecture.